Thank you very much for the invitation to give this talk. I will talk about Kramers-wannier duality in non-abelian Ising models from SymTFT. Kramers-wannier, which is usually presented as a duality between a low temperature theory and a high temperature theory, is an important aspect of Ising models, usually with abelian global symmetry. Today, I would like to talk about how we can generalize this definition of Ising models to have um, finite group non-abelian symmetry or even non-invertible symmetry, and how we can generalize the notion of Kramers-wannier to these theories. To that end, let me start with the abelian case to kind of set up the notation and explain the motivations behind the construction that I will talk about later. So for me, sigma will denote the 2D lattice on which I will define my models. And V, E, and F are going to be the sets of the vertices, edges, and faces of this lattice. S and T for any edge will denote the source and the target. A will refer to the abelian group, and I will refer to the space of fields, which are functions valued in this abelian group defined on the vertices as A to the V. And I will allow different Boltzmann weights at different edges. And this, for any edge, a Boltzmann weight is simply a complex valued function on my group. My notation for the partition function is as follows. So here, A refers to the global symmetry of my theory. Sigma is the lattice on which I have defined the model, and theta refers to the Boltzmann weights or the coupling constants. And as usual, I have the partition function is defined as a sum over all field configurations and then a product over all the Boltzmann weights. The simplest case is when A is Z2, which I take to be multiplicative, and when all the Boltzmann weights are the same, irrespective of the edges, and they have this exponential form where beta is the inverse temperature. In this case, the partition function takes this familiar form where I have a sum over Z2 valued fields. And in the exponent, we see the action for the Z2 Ising model. Now, let's look at the Kramers-wannier duality in abelian models. It should be emphasized that the classical statement of the Kramers-wannier duality applies when the underlying lattice is simply connected. In that case, we can compare the partition function of an Ising model with global symmetry given by A to the partition function of another Ising model whose global symmetry is A check, which is that if so if we're on a simply connected lattice sigma, then the partition function of the Ising model with A global symmetry can be compared with the partition function of another Ising model, which has a symmetry given by A check, where A check is the Pontryagin dual of A. And this Ising model is on the Poincare dual lattice with dual weights. So these dual weights are simply functions on the dual group that are given by Fourier transforming the original weights. And instead of writing this as an equality, I'm writing this as an approximation, mostly because there are some factors here that depend on the background fields, but there are some fixed factors and not going to be very important. So for example, if we look at the Z2 case, then as I said, that I can take the Boltzmann weights to be just exponential for all the edges, in which case the Fourier transform of this function is another function of the exponential type, where I simply replace beta there should have been a beta here by another factor. And so these factors, these overall factors are responsible for this approximation sign. But the main point is that we can compare two Ising models, both of which have Z2 global symmetry. Well, of course, for any abelian group, the Pontryagin dual is isomorphic to the original group. And they have temperatures related by these this kind of functional forms. And if we look at the temperature instead of the inverse temperature, then this duality maps two theories at two different temperatures. One is at low temperature and the other is at high temperature. And if the lattice is such that it is self-dual, then we can really say that it's the same theory at two different temperatures that are dual to each other. All right. Any questions so far? Okay. Now, so when we say that a theory has a global symmetry, it is equivalent to saying that we can couple this theory to background gauge fields. So let's look at the perspective on global symmetry in case of the Ising model. So let me introduce the quotient complex of forms on my lattice. So my lattice is two-dimensional, so I can introduce 0, 1, and 2 forms. So and they are basically just functions, a-valued functions on the vertices or the edges or on the faces. And I can define some differential between these functions. So for example, d0 sigma, if sigma is a 0 form, then d0 sigma is a 1 form. And for any edge E, the element of the group A that I get is the difference between the two elements at the end of the edges. And for any one form A, I can draw something. So suppose this is a face, and I have A1, A2, A3. Then D1, A, F is just A1, A2, A3. So I pick up the values of A from the boundary of the face. Okay. Now, the space of closed one forms are in the kernel of D1, and these are going to be my background connections. And the Ising partition function coupled to a background gauge field A is simply a modification of the original Ising partition function of this one by the insertion of this gauge field at each edge. That's all. Okay. Now, so what do the gauge transformations look like? So suppose A is a gauge field, then given n is 0 form, which is an a-valued function on the vertices, the gauge transformation of A is simply A times the d0 of tau, where A times d0 of tau evaluated at any edge is just this expression, where A is coming from this A, and d0 tau gives this part. And of course, the partition function is invariant under any such gauge transformations of the background connection. So this partition function evaluated at this background is the same as another partition function evaluated at a background that differs by a gauge transformation. So we can consider gauge equivalence classes where we quotient out by this kind of modification of the connection. So the moduli space of background flat connections is given by the first cohomology valued in A, which we can compute. And this is simply given by homomorphisms from the fundamental group of my lattice to A, which if I take my lattice to be the 2 torus, then the fundamental group is Z times Z. And so this homomorphism group simply gives me 2 copies of A. And in physical terms, we can think of these 2 copies of A as labeling the holonomies of the background connection along the 2 non-contractible cycles of the torus. Okay. So from now on, I am always going to consider my lattice to be a lattice version of the 2 torus. So everything I'm going to say can be generalized to arbitrary 2D surfaces with arbitrary fundamental groups. But it just gets more complicated, but basically the ideas remain the same. So here what I want to motivate is that any background connection is equivalent to certain topological operators. So what do I mean? So let's take this concrete example of a lattice version of a torus. So this box represents a torus where these 2 blue sides are identified and the 2 red sides are identified. And these black lines are my lattice sigma. And the gray lines, they constitute the dual lattice sigma check. Now, so far what I have been saying is that a connection, an element here, for example, this is an assignment of an element of A to each edge. In that vein, so when I do not write any element here, for example, so I can think of there being the identity element. Now, suppose I have a background connection, which is characterized by the fact that it has holonomies H1 and H2 in the 2 non-contractible cycles of the torus, where H1 and H2 are elements of A and A. So then I can simply label this edge with H1, this edge with H1, and this vertical edge with H2, and this vertical edge with H2. So then, for example, if I want to go from here to here, I have to pass through this edge, which has H1, giving me the total holonomy of H1 in this direction. Similarly, if I take any path in the vertical direction, there will be one H2, giving me the holonomy H2. Now, this connection can be characterized by putting two line operators on the dual lattice. And so these line operators are supported on the non-constructible cycles beta 1 and beta 2 of my dual lattice sigma check. And they are labeled by the two holonomies H1 and H2. And the idea is that whenever an edge of the original lattice intersects with a topological line, I label that edge with H1 because this was labeled by H1. And similarly, this intersects this edge, which is therefore labeled by H2. So basically what I'm trying to say is that the information of this background connection that has holonomies H1 and H2 is equivalently encoded in line operators supported on the dual lattice, on the non-contractible cycles of the dual lattice, labeled by the holonomials. And so we can think of these line operators as analog of a 2th operator in the gauge theory because they're modifying the background connection. And different non-equivalent insertions of these kind of line operators will give us different topological sectors with respect to the global symmetry. Yeah. Any confusion so far?
If you change the H1 and H1, you take two different cycles, you get something different. I will imagine you label the.
Sir, could you repeat the question, please?
If you change the H1 and H2, you take out cycle.
Yes.
You will get, okay. So it depends on the choice you make at the beginning.
So I can modify the cycles in the sense that, I mean, I can deform the cycles continuously. So for example, so here I just went straight down this direction, but I could go something like this. And that would be an equivalent line operator. I mean, it will be the same topological sector. So the line operator is only defined by the homology classes of these cycles, not by the exact cycle itself. But if I change H1 and H2, that will give me a completely different topological sector. When there is no gauge transformation which changes H1 and H2, but there are gauge transformations that will change the support of this line operator from this to something like something else, I guess. Does that answer your question?
Yes, thanks.
Okay, great. All right, so then we can ask, how do we, given a global symmetry, it's natural to ask how we can gauge the global symmetry. And so the gauging of a global symmetry is basically the same as summing over all background gauge fields. So the partition function that we have, so we can think of this partition function as a function on the moduli space of flat connections, labeled by H1 and H2, the two holonomies in the two non-contractible cycles. And so summing over these holonomies is equivalent to gauging this global symmetry. But there is some choice to be made when we are summing over background connections. So basically, whenever we want to sum over these background connections, we have to introduce two extra parameters that are labeled by elements of the dual group. And the reason is that a sum over background connection looks like this. So we have our partition function of the theory with a global symmetry in the background given by H1 and H2. We can multiply this by chi1 H1, chi2 H2, where chi1 and chi2 are arbitrary elements of HA. And then we can sum over all the background holonomies. And this constitutes a gauge invariant quantity, which we define to be the partition function of a theory where we have gauged the global asymmetry, but we have gauged with the choice given by chi1 and chi2. And in this line, I'm simply pointing out that the partition function of this theory in this twisted sector is equivalent to considering the expectation values of these two topological operators, in the untwisted theory. So these two perspectives are the same. The theory in the twisted sector or the theory in the trivial sector, but with the insertion of topological line operators. And notice that chi1 and chi2 are valued in HX times HX, which is simply the first cohomology valued in HX, which also happens to be the labels for these topological sectors of a theory that has global symmetry HX. And that is, of course, not a coincidence. We know that if we gauge a global symmetry A, we gain a new global symmetry given by the Pontryagin dual of A. And therefore, the sectors of this gauge theory should be labeled by H1 valid in HX. Okay. So now that we have a better understanding of the non-trivial topological sectors, let's revisit the abelian Kramers-wannier duality. So on one side of the duality, so this is where we start from. So here we have a theory with a global symmetry on the lattice sigma, with some Bures-van weight given by theta, and in a non-trivial topological sector given by H1 and H2. So starting from here, we can perform a gauging. So we can gauge the entire global symmetry, and then we find a gauge theory. So this is my notation for a gauge theory, that A mod A, and I remember the choices made while gauging. But in addition to gauging, we can also perform another operation, which is simply replacing the local degrees of freedom by their Pontryagin dual. So what I mean is that in this theory, my degrees of freedom were valued in A, right? Because my fields were the fields over which I summed, they were elements of this set, synapse from V to A. And by Boltzmann weights, this theta E, this was a function on A. Now, I can perform, in some sense, a trivial operation, which is that I can replace this kind of degrees of freedom by dual degrees of freedom valued in HX. I cannot write a check and V in a different place. Maybe I should, let's not write this. Okay. And right, so if we simply change my local degrees of freedom, then that amounts to performing a Fourier transformation for my Boltzmann weights. This does not change the partition function in any significant way, in the sense that it is still exactly the same partition function, but I'm simply writing it using different coordinates in some sense. And therefore, this partition, so whatever I will find after performing this local Fourier transform on this partition function is going to be labeled by the same topological sectors. Nothing has changed. It's the same theory, but written in in terms of different degrees of freedom. And in fact, this was the operation that originally led to the Kramers-wannier duality on a simply connected lattice. And the reason that the simply connectedness is important is that if we are careful about the non-trivial topological sectors when we are on a torus, we will find that after performing a local Fourier transformation on this partition function, so let's say we take a partition function that looks like this with a global symmetry. We do a local Fourier transformation. What we will end up with will not be something that looks like this, but rather it will be something that looks like this with HX, but summed over all background connections. So, in fact, what we'll find after doing the Fourier transformation is something that will be the partition function of a gauge theory, where the gauge group is HX. That's what I'm trying to say here, that changing local degrees of freedom takes us from a theory with global symmetry and no gauge symmetry to a theory that has only an HX gauge symmetry. And if we are careful about these labels that we find, we will see that this is simply the refined gauging, where these parameters are now the parameters for the refined gauging. Similar thing can be done here as well. So this gauge theory is dual to another theory that has HX global symmetry. And the original statement of Kramers-wannier compared two theories of this type, one with a global asymmetry and the other with a global HX symmetry. But as we can see here, if we do this carefully, then this involves gauging and then a Fourier transformation. So Fourier transformation doesn't do anything to the partition function. It's still the same partition function. But gauging is basically by force changing the theory. Therefore, if we just take this theory in some arbitrary sector and this theory in some arbitrary sector, their partition functions will not coincide and those theories will not be dual to each other. We have to find a precise mapping of topological sectors for these two theories to be the same. And the mapping is given by this formula, which is that, so here we have, we are talking about the theory with global asymmetry. And we are in a sector where we have non-trivial holonomies H1 and H2 in the two non-contractible cycles of my torus. And on the dual side, we have a sum over all possible topological sectors with various weights. So here alpha 1 and alpha 2 are also non-contractible cycles on the torus, and O check are Études operators of the dual theory. So here we are in a sector where we have fixed holonomies in both directions. And here we are in a superposition of sectors. So no fixed holonomies in any direction. Rather sum over all possible holonomies with various weights. Notice that if here we started in the trivial sector, where there's no holonomy in any direction. So H1 and H2 are both identity operators. So then for any chi1 and chi2, when evaluated on the identity element, it just gives me 1. So the trivial sector on one side corresponds to the equal weight superposition on the other side. Okay. Any questions before?
Go ahead.
Okay. Now, what we would like to know is how to generalize this story. So how to consider Ising models that have more interesting symmetries than just abelian symmetries. So for example, non-abelian finite groups or categorical symmetries. And then how we can do this process of gauging and what does Kramers-wannier look like? So that's going to be the main topic of the talk. So here I'm going to skip a few pages. I think these are quite elementary. So yeah, as I was saying, that the main point is that we want to generalize the global symmetry from abelian to categorical. And so from the general story about generalized symmetry, we know that the topological line operators in a theory that correspond to these symmetry implementing operators, they can be labeled by objects of a semi-simple spherical fusion category. So these are literally these line operators, these ones. So here we were talking about a theory that has a global symmetry, and we argued that this theory supports topological line operators labeled by elements of A. And so when we have a theory with global symmetry given by any group, any non-abelian group G, these line operators will be elements of G, or more generally elements of a spherical fusion category. And so junction, and these line operators come with some consistency constraints. So for example, whenever there is a junction of line operators with various levels, or so G1, G2, then these junctions are labeled by elements of the Helm spaces from the product of all the elements incoming at the junction to the identity element of my fusion category. And if this Helm space is empty, then such a junction is not permitted. So if these are literally group elements, then this Helm space will either be empty or it will only have one element. So we don't really have to worry about a non-trivial Helm space, but in general, there can be multiple maps from this product to the entity. So some of the fusion categories that will be important for for the talk are, for example, vec-G, which is the category of G-graded vector spaces. Simple objects of this category are labeled by the elements of the group. And so this category is basically the categorified version of the group itself. So in the uniform language of categories, whenever I have a theory with G global symmetry, the underlying category will be vec-G. A closely related category is rep-G, which is a category of finite dimensional representations of G. Simple objects of this category are irreducible representations. Inverse in this category means dual representation, and in general, this is a non-invertible category. So these two are going to be the most important examples. So for example, in the abelian case, so I had this duality between A and AHEC, the Pontryagin dual, and that is, in the non-abelian case, that literally is replaced by the non-abelian group G and the set of irreducible representations of G, which is G hat. And these two things are the simple objects of vec-G and rep-G respectively. Just for example, another category that also shows up at various occasions is the Ising Z2, which is the symmetry of the Z2 Ising model at critical temperature. It has three simple objects given by some simple relations. So the monoidal structure in vec-G is of course given by the ordinary group multiplication. And the monoidal structure in rep-G is given by simply the tensor product of modules. Okay. And this defines the monoidal structure here. All right. Okay. So how do we define an Ising model with this kind of enhanced symmetry? And the trick to doing that is utilizing something called a symmetry topological field theory, which has recently become very popular. So what is the idea? The idea is that, so we are trying to define a two-dimensional theory, a 2D Ising model with certain symmetry. And for doing that, we are going to consider a three-dimensional theory. So this three-dimensional slab with boundaries is what we're going to study. And in the bulk of this 3D object, we are going to put a topological quantum field theory, which I'm writing as T-sim. And at this red boundary, we're going to impose some boundary conditions that is going to be consistent with the topological symmetry of the theory. And at this blue boundary, we're going to put some dynamical boundary conditions that is going to break the topological symmetry of the TQFT. Now, we know that if we consider a manifold, a space-time manifold with boundaries, and we impose certain boundary conditions on one end, and now if we perform a path integration in the bulk, then we're going to produce a state in some Hilbert space at this boundary. So there will be a Hilbert space assigned to this boundary, and the path integration here will produce a state. And since this boundary condition doesn't break the topological symmetry, I'm going to call the state produced here the topological state. Similarly, by performing path integration in the bulk here, we're going to produce a state at this boundary, which is not going to be topological, and I will refer to as a dynamical boundary, a dynamical state. Now, we can consider the inner product between these two states, something like this, which geometrically boils down to gluing these two halves to produce a single 3D object with two boundary conditions. And since this theory is topological in the bulk, I can effectively shrink this direction, producing a 2D version of this theory. So there is a 2D effective description of this 3D theory, and that 2D effective description is going to be my desired 2D theory. So this inner product, I will treat this as the partition function of my desired 2D theory. Okay, so this is very schematic. But of course, ultimately, the claim is going to be that the Ising model that I want to write down is going to come from a construction similar to this, where I have some 3D TFT here and certain boundary conditions here, so that when I evaluate the partition function of the 3D theory, that is going to give me the partition function of the Ising model with certain symmetries that I want. Okay. So some properties of this construction is that there is separation of kinematic and dynamical information. So for example, so given any symmetry or fusion category C, there is a universal choice for the bulk TQFT, and which comes equipped with its topological boundary conditions. So to determine this TQFT and its topological boundary conditions, we do not need to know anything about the theory other than the global symmetry. So this part doesn't know anything about dynamics. It's purely kinematical object. And all the dynamical information in terms of these Boltzmann weights or coupling constants or other background fields, they are all encoded in this boundary condition. So the first question that we must answer as a proof of concept is that can we all necessarily write down the partition function of an Ising model as an inner product between two states in some Hilbert space? So we can check this in case of the simplest theory, which is the abelian Ising model. So let's again consider the abelian Ising model with global symmetry A. So let L to A be the space of square integrable functions on A, which has the basis given by the elements of A. And the Hilbert space structure of L to A is defined by an inner product like this. So then we can define the lattice Hilbert space by taking a copy of L to A for each edge and taking a tensor product over it. Now, a generic product state in the Hilbert space, I'm writing it as something like this. So for each edge, I pick an arbitrary function on A, which is going to be my Boltzmann weight. And then I have a distinguished family of topological states that are labeled by two group elements. And those states are going to look like this. So again, so there's a sum over zero, A valued zero forms, and then a product over all the edges. And then this connection, and then this D0 sigma type thing. So just from observation, we can see that if we take an inner product between this and this, we are going to produce precisely the partition function of my 2D Ising model in a twisted topological sector, twisted by the holonomies H1 and H2. And this is inner product of this and this state. So the partition function of the asymmetric Ising model in a twisted sector can indeed be written as an inner product between two states. So we can ask why these states are being referred to as topological. Well, so we can compare with something interesting. So we can define the 2D toric code for the Hopf algebra, the group algebra of A on our lattice sigma. And if we do so, we will find that these states, when we vary H1 and H2, they span the ground state Hilbert space of this toric code. So they are, in fact, topological in the sense that they are ground states of the toric code. And in fact, this correspondence between these topological states and the toric code ground states, it generalizes directly to non-abelian case as well. We can consider a G-symmetric Ising model and the toric code based on the group algebra of G. And again, there's a one-to-one correspondence between ground states and topological sectors. Okay. Any questions so far?
Sorry, these states that you say topological, these are not ground states of the Ising Hamiltonian, right?
No, they're ground states of the toric code Hamiltonian.
Okay. Okay.
Okay, so now let's try to be a bit more concrete about how to exactly get the Ising model itself. So the proposal is that we need to consider the three-dimensional topological quantum field theory known as the Turab-Viro-Bartlett-West-Bury theory, which is defined based on a spherical fusion category, which will be called the input category C. So in the bulk, we have this 3D TQFT. So this is 3D. And so this theory has a distinguished set of topological boundary conditions. And at this red boundary, we can put any one of these topological boundary conditions. And at the other end of this 3D slab, we can basically put any arbitrary boundary condition that we want. And because of the topological nature of the theory, we can shrink this and get an effective 2D description. And based on what kind of boundary condition we put here, we will get different dynamics here. And of course, the claim is that we can choose this boundary condition in such a way that this dynamics is simple enough that it can be reasonably called an Ising model, by which I mean that it's some kind of nearest neighbor interaction that depends on the differences between degrees of freedom at the endpoints of the edges. But we have the freedom to consider much more general theories here by considering these to be completely arbitrary. And if we have if we have line operators in the bulk, they will be sandwiched and become line operators in this effective 2D theory. Now, so some results that people have discovered about this Bures theory is that the topological boundary conditions of this theory are labeled by the module categories of C. So whenever I write Bm, this M will be a module category of C. And any fission category C, spherical fission category C, the line operators in the bulk of this Bures theory are going to be labeled by objects of the Dirichlet center of C. However, not all of these line operators will survive the sandwich process, because based on the boundary condition that we choose, mainly based on the choice of this module category, some of the line operators from the center will condense, and the rest will survive as topological line operators in the effective 2D theory. And these surviving line operators will determine the global symmetry. Because again, recall that the topological line operators in our 2D theory, or the labels of the topological line operators in our 2D theory, correspond to elements of our global symmetry. And the result here is that the line operators that survive this sandwich process, they form this Morita dual of C with respect to M, which is defined as the end-effector category of M with respect to C. So again, just to recap the steps in constructing this Ising model, we're starting from the input category of the bulk TQFT, which is some spherical fission category. Then we have to choose some topological boundary conditions labeled by module category M. And there are different choices of module categories, and these different choices will correspond to basically gauging different subgroups. Well, I cannot say a subgroup because it's not necessarily a group, but different subsymmetries of the global symmetry. And so once we have chosen our input category and the module category, we can determine the topological line operators in the effective 2D theory, which in turn determines the global symmetry of the 2D theory. And that is always going to be given by the Morita dual of C with respect to M. And the different topological sectors. These of course, is a non-trivial statement that I haven't proved, but it can be proved that different topological sectors in this effective 2D theory are labeled by objects of the center, the Dirichlet center of the global symmetry category. Now, to connect with some other literature, so if we keep our input category C fixed, and also the dynamical boundary condition fixed, and vary the topological boundary condition, so meaning that we are basically gauging different subsymmetries of the same theory, then all the theories that we produce in this way, they form something called an orbifold groupoid. And the global symmetries of all the orbifold groupoids are Morita equivalent to each other, because the Morita dual of C with respect to different module categories are Morita dual to each other. So let's look at an example, perhaps. Suppose as our input category, we take vec G. So this is the case where we're really just talking about a theory with global symmetry given by some non-abelian group G. Now, suppose as the module category, we also choose vec G. This corresponds to gauging nothing. So that the global symmetry literally is, again, just the global symmetry given by this non-abelian group G. And then in this case, the center of our global symmetry category, is something called the commuting variety of G. So what is the commuting variety? It is a pair of commuting group element of G quotient by their adjoint action. So again, this is simply, so if we have this torus, then we can put line operators, topological line operators labeled by G1, G2. For abelian groups, we don't have to worry about what we put here. But for non-abelian groups, we can only put G1 and G2 if they commute with each other. And that's why we have this commutativity constraint. And we have to quotient by G because changing both G1 and G2 by an adjoint action corresponds to an action of a global symmetry. So it doesn't give us anything new. If as a model category we take VEC, so VEC is basically VEC G, but we have kind of forgotten the action of the group. So this is basically just a category of fine-dimensional vector spaces. Then it turns out that this is equivalent to gauging the entire global symmetry G, which gives us a new global symmetry given by the representations of G. And objects here are the sectors of this area labeled by representations of the Dinfeld center of G. We can also choose some model categories corresponding to subgroups of G, which amounts to gauging subgroups of G. And then the global symmetry is something like quotient of G by whatever we have gauged and representations of whatever we have gauged. I mean, this is very schematic. Literally taken, it doesn't mean anything, but I'm just kind of pointing out that the global symmetry is kind of the quotient and new representations of whatever we have gauged. And if we again go back to the abelian case, then the formatting variety is just A times A, and this is just A check times A check, as we have seen previously. Okay. Any questions so far?
We are good.
All right. Okay, great. So now that we have kind of established how we should think about different topological sectors and the gauging different subsymmetries of our Ising model with a non-trivial symmetry, so how should we think about Kramers-wannier duality? So previously we saw that in the abelian case, Kramers-wannier duality was achieved by performing two operations one after the other. One was gauging some kind of symmetry, and the other was performing a Fourier transformations of the local degrees of freedom. So we have already talked about gauging in the categorical sense. So what is the analog of local Fourier transformation? So the point is that when we consider this kind of 3D TQFT, this Tura view TQFT has something called the mirror symmetry. So this symmetry exchanges a TQFT based on a category C with the TQFT based on a category which is more orthodual to C with respect to the category VEC. Yeah, and again, VEC is just the category of fine-dimensional vector spaces. And so this symmetry does not only change the input category, but it also acts in a very specific way on the topological boundary conditions. So given a module category M of C, we will have a specific module category M check of C check. And similarly, we also have to modify the dynamical boundary condition by essentially replacing the Boltzmann weights with their Fourier transforms. And this operation of whatever is analogous to the mirror symmetry for the TQFT, 3D TQFT, is the generalization of the local Fourier transformation that we saw in the abelian case. So a special case is that if we start with VEC G, so we are talking about Ising model with G global symmetry, then the symmetry or this duality exchanges VEC G with Rep G. So now we're talking about an Ising model whose local degrees of freedom are given by representations of G as opposed to elements of G. And of course, we can still call these local Fourier transformations because in the original theory, our Boltzmann weights are functions on the group G, and the analog of Fourier transform for non-abelian finite group changes a function on G to a function of representations of G, meaning that exchanging these two is analogous to doing a Fourier transform. Okay. So then, what is Kramers-wannier? So Kramers-wannier again is the composition of two processes. One is gauging, and the other is this local Fourier transformation. So here again we start at this corner. So here we're talking about an Ising model whose global symmetry is given by some category C check M. So this notation implies that we constructed this Ising model by considering a Bures TQFT whose input category was C and M was our choice of topological boundary condition. And the topological sectors of this series are labeled by center, the neutral center of this global symmetry category. And as we discussed, that gauging really means that changing the topological boundary condition, the module labeling the topological boundary condition. And these series are the topological sectors of the series are labeled by, again, the neutral center of this. And this Fourier transform, which is simply the action of this mirror symmetry, exchanges our input category C with C check with respect to vec, and the module category M with M check, giving us a new global symmetry. Well, actually, this must be the same global symmetry as this one, right? Because this is the same theory as this. It's just a dual descript comes sample this. But when we combine both gauging and a mirror symmetry, we encounter a new type of theory whose sectors are labeled by the Drinfeld center of C check N, and here the sectors are labeled by Drinfeld centers of C check M. And again, we want to say that these two theories are dual in the sense of Kramers-wannier once we find the proper mapping of sectors between these two theories.
This identification of topological sectors with elements of the Drinfeld center of the symmetry, is it true on every lattice, on every sigma, or special to the torus?
Nafiz? We're off? Can you hear us, Nafiz?
No.
Yeah.
It's not my fault.
Yeah. But it was a good question.
It was too hard, bro. Well, he didn't know the answer. Yeah, that's why.
Hello.
Yes, we are here, but we can't see your slides anymore.
Okay. Yeah, I'm trying to hear again.
Okay, good.
There was a question from the audience.
Yes, please. Could you repeat the question, please?
Yes, I was asking if this identification of topological sectors with the elements of the Drinfeld center of the symmetry is special to the torus lattice, or is instead is general?
Sorry, it's special to what?
It's special to the choice of sigma being the torus lattice.
No. It's general. Sigma can be anything.
Okay.
Nafiz, just
okay.
to, sorry to interrupt you, I think we have,
Yes.
we are almost finished with time. So there is, like, say, 10 minutes for questions. So
Okay.
You can perhaps wrap up a bit.
So I think I can wrap up in 5 minutes.
Okay.
Okay, so let's see. Okay, so let me just give an example of how these sectors are mapped. So for example, if we take as input category vec G, and we consider two module categories, vec G and vec, so then on one side, we are considering a theory with global symmetry given by G, and on the other side, we're considering a theory whose global symmetry is given by rep G. And that the key to finding a map between sectors is to notice that the sectors of both of the series are labeled by the Drinfeld center of vec G. And elements of the Drinfeld center of vec G are pairs where C is a conjugacy clause of G and V is an irreducible representation of the centralizer of this conjugacy clause. Now, let's take an example where I take the trivial conjugacy clause and then any representation of the group G. So this element of the Drinfeld center of vec G labels a superposition of sectors on the theory with G symmetry, where we have a line in one non-contractible direction labeled by all possible group elements, and the weight is simply given by the trace of this group element taken in the representation V. And on the other side of the Kramers-wannier duality, we again have a superposition of different sectors where we have lines in both directions. So in one direction, the line is fixed. It's labeled by the representation V. And on the other side, the line, we have a sum over all irreducible representation of G, where the weight is given by the dimension of that representation. So as we can see that the mapping of the sectors is quite non-trivial. Let's see. So far I have kind of given the abstract definitions of how to think about gauging and Kramers-wannier duality, et cetera. But how do we actually check that these claims are correct and how to actually compute the partition function? So for that, we use a tool called tensor networks. So perhaps I will not go into too much detail, but the idea is that, so we represent each tensor as a diagram. So where each vertex is a tensor and each of its edges are the indices. So for example, this is a tensor with 3 indices. So T, rho mu, et cetera. And when we have an edge connecting two vertices, that simply corresponds to contraction of tensors. So this, for example, has a bunch of tensors contracted and some indices uncontracted. So when we want to compute the partition function of a SymTFT such as this, so we create these topological and the dynamical boundary states as 2 different tensor networks. So this part is this part, and this part is this part. So what we do is that we set up some tensor network. So each vertex represents a tensor, and each edge connecting to vertices is a contraction of some indices, and each edge not connecting to vertices is some free index. So at the end of the day, this will be a huge tensor where I have free indices corresponding to these vertical edges, and this will be another tensor with indices corresponding to these vertical edges. And then simply contracting these edges, I will find some number, which will be the partition function. So where do these tensors come from? These tensors is basically part of the data that defines the categories that I was talking about. For example, if my input category is C, then the C has some a certain structure defined by tensors. For example, the C has some simple objects, which can be the tensor product of the simple objects can be decomposed into direct sum of simple objects with multiplicities, the multiplicities being the home spaces. And then if I want to compare what happens if I take the tensor product of 3 different simple objects, but in different order. So I'm checking the associativity. So then I know that these 2 things have to be isomorphic, but the isomorphism can be non-trivial. So basically, I expand both of these things in terms of simple objects, and then I need to specify the isomorphism between the multiplicity spaces. So I introduce some symbols which give me the isomorphisms. And the point is that regardless of which category I'm talking about, so these things can come from some arbitrary spherical fitting categories. But these home spaces are always vector spaces. So that these isomorphisms that I'm specifying, they're always linear maps. In other words, tensors. Similarly, when I have model categories, so again, suppose M is an object in the model category, and these are objects in my input category. So then I can compare this with this. So where first X acts on M, and then this acts here. Or I can take the tensor product and then act here. And if I want to establish the isomorphism between these 2 things, again, I have to specify some linear maps. So the point is, so whenever I have something like this, so if I zoom in here, for example, well, that's basically this picture. So 3 edges on the bottom plate and 1 vertical edge. So this tensor is literally given by these F symbols that define these kind of isomorphisms. The details are not very important. What I'm trying to convey is that there's a specific concrete prescriptions for attaching tensors to each vertex so that we can perform all these contractions and ultimately get a number, which is the partition function. Okay, so that's basically how we compute these partition functions. So to kind of summarize, so composites of these tensors are used to evaluate the tensor network, giving the partition function of the Ising models. In the topological side, we only need the F symbols to conserve the tensors. Whereas on the dynamical side, we need the F symbols, but we also need the data of the Bures-sur-Yvette weights. Of course, I have not specified how to use the Bures-sur-Yvette weights, but there is a way. And then finally, the partition function is computed by the tensor contraction of the 2 tensors that we created from the upper and the lower half of this big network from here and here. And since this is just a matter of matrix multiplication, we can simulate these things in computers. Okay, so summary. The Ising model, we can naturally formulate it in a way so that it has categorical symmetries, not just Z2 or abelian symmetries. These models can be realized as the boundary theory of a three-dimensional Bures-sur-Yvette TQFT. And dualities of the bulk theory result in dualities of the boundary theories as well. And the computations of the partition functions and the verifications of these dualities boil down to computing tensor networks and checking that we have the same numbers. So what are some directions that we can pursue? So here, okay, I should clarify that maybe these things are already known. I'm just not familiar with the literature that well. But it seems that the precise descriptions of dualities of these Bures theories, and when I say duality, I really mean the duality of boundary conditions along with the mapping of operators in the series. This does not seem to be that well organized yet. Okay, but maybe some people know, I just don't know. And of course, we don't have to be stuck into dimension. We have, at least in principle, the definition of a fully extended TQFT. So we can try to use that to generalize this picture to higher dimensions. And again, find the duality mappings of boundary conditions and topological operators. All right, so that is all what I wanted to say. Thank you. If there's any question, please.
Yeah, thanks a lot. So I guess we have perhaps some time for one or two questions. So please.
Okay. Did you work out any concrete example? Like you chosen some boundary symmetry and worked out whether these has dualities or not?
So the duality between the G-symmetric theory and the red B-symmetric theories, we actually computed that explicitly in a way. I mean, we explicitly showed that the partition function of the G-symmetric theory with certain topological line operators is equal to the partition function of the red G-symmetric theories with the dual line operators. I mean, the partition function does not boil down to a simple closed expression, but we can manipulate the partition function, the tensor network form of the partition function in a way that we can maintain the equality of the partition functions at each step.
Okay.
Any other question? Okay, so well, thanks a lot again.
Thank you very much.